Hey, welcome back. In this video, we're going to discuss matchings. And we've seen these in class earlier, but today we're going to talk about how to find the largest matchings in graphs. We're going to talk a little bit about perfect matchings, and we'll also see some applications of matchings. So matchings, there are a bunch of edges with no common vertices. More specifically, if you are given some graph G, a matching of that graph G is just a set of edges in G which have no common vertices. And we can define a bunch of different kinds of matchings. So one kind of matching that we will look at today, and we'll see an algorithm to find this kind of matching, a really easy algorithm. This kind of matching is a maximal matching. And a maximal matching is just a matching that is not a subset of any other matching of G. And there's a special kind of maximal matching. And this special kind of maximal matching, we call it a maximum matching. A maximum matching is just a matching of maximum size in G. And one thing I'm going to mention here, which is pretty obvious, and I already said it kind of, every maximum matching is a maximal matching. And this is because a maximum matching, it's a matching of maximum size. So it can't be a subset of any other matching in the graph, because otherwise the matching that it is a subset of would be a larger matching, and then it wouldn't be a maximum matching that we're talking about. So this is why every maximum matching is a maximal matching, because it's not a subset of any other matching in the graph. And I thought it would be good to look at a few examples. So let's consider the first example. We've seen this one a bunch before, the star graph. I'll put this, I guess, up top. So it'll be some K1n, some star. And if we put any edge of this star in the matching, like for example, we'd stick that one in the matching, then unfortunately we cannot put any other edges in the matching, because all of the other edges in the star have vertices in common with that edge. So any two edges in a star have a vertex in common. The vertex they have in common is the center of the star. So maximum matchings in stars have size 1. Maximal matchings have size 1. In fact, all non-empty matchings have size 1 in the star. So the star, it's not very exciting what happens in the star. Kind of interesting, but not much going on there. Okay, let's look at another one. Let's consider a complete graph. I'll draw a pretty small one so it doesn't take forever to draw its edges. We'll do a K4. It'll have some crossing edges, unfortunately. And if we want to find a matching in this complete graph, we can take this and this right here. So that gives us a matching. There are smaller non-empty matchings in there, So another matching of that complete graph of order 4. We could have just taken a single edge, like just that one. So that's also a matching of that graph. And we can see that the maximal matchings, if you take a matching of size 1, like we did over here, by symmetry, the way we've drawn it, any matching we pick of size 1, we can draw like that by symmetry, just by putting the 2 vertices for the edge of that matching on the left side of the picture, like I have here, whatever the vertices are. Like they're called U and V, then there's their names right there. But if we have an edge in a matching, just a single edge in this matching of K4, we can always add another edge to it. We can add the edge that is on the other 2 vertices in the K4. So the maximal matchings in K4 will have size 2. They can't have size 1 because any matching of size 1 won't be maximal because we can add an edge to it and we still get a matching when we add that edge. And the maximum matchings of K4, of course, also will have size 2. You can't have any size greater than 2 because you would need more vertices in the K4. You can only use each vertex at most once in the matching. Let's look at one more, because this one, I feel like this one is a little more interesting than the other 2. We'll look at a nice small path. I'll put it down here, actually. We got all this nice space down here. We'll do a P4. So P4 right here. We had our K4 up here. Okay, I'm going to draw it twice. Here's another P4 down here. So we have these 2 copies of P4, and I'm going to draw 2 different matchings on them. So on that first P4, I'm going to put a matching that uses the 2 outermost edges. So we'll have this edge right here, that edge right there. And we can see that that matching, it is a matching. And I'm going to draw a different matching on the bottom one. And both of these matchings, they are both a certain type of matching we see up here. They are both maximal matchings. So both are maximal. We can see that pretty simply. So we can look at this first one up here, second one down here. That first one up there, we can see that there's no matching that is a superset of this matching, because in order to get a larger matching than this one, we would have to add this edge to it. And adding that edge to it would give us something that's not a matching, because we would have edges that have vertices in common, including that vertex and that vertex. So this one up top is maximal. More interesting, though, is the bottom one is also maximal. So that bottom one, if we wanted to find some superset of edges for that is also a matching, we could either add this edge or we could add this edge. If we tried to add those edges, though, we would end up with something that's not a matching, because both of those edges have vertices in common with this single edge in our matching right here. So those 2 vertices. So we can't add any more edges to that matching the bottom and still get a matching. So the matching the bottom, even though it's smaller than the one at the top, it is still maximal. So they're both maximal, so that's kind of interesting, even though they're different sizes. And of course, only one of them can be maximum because they have different sizes. And the maximum one is this one up top, and the one on the bottom is maximal, but not maximum. So those are just a few examples of matchings in some families of graphs that we have seen before. So there's a really interesting application of matchings. And I mean, there's multiple applications. So you can look at certain applications with matching like students up to courses, this kind of thing. So a lot of people do applications in that sort of vein, like matching things up with other things. And you could say this application is kind of like that too, but I think this one's especially interesting. So this application is kidney donation. So when someone needs to get a kidney transplant, some kidney transplant recipient, they will usually enter the process for matching up with people paired with some friend or relative who's willing to donate a kidney. But usually the problem is that whatever friend or relative is willing to donate the kidney, they're not going to be a match for the person that they want to donate it to, like their friend or their relative. So the two of them enter the process, someone who needs a kidney and someone who's willing to give a kidney. And like I said, usually these pairs are incompatible. If they get really lucky, they're compatible, and then you only need to do the operation on the two of them. But if they're not compatible, you can still make it work. And how it works is they have to find another pair with a donor and a recipient. And the requirement, so we can think about it like we have a pair, a D1 and R1, donor 1, recipient 1. And we have a D2 and an R2, donor 2 and recipient 2. And donor 1 must be compatible with the other recipient. And donor 2 must be compatible with recipient 1. So donor 1 is not compatible with recipient 1. So D1, R1, not compatible. Same with D2, R2. But D1 and R2, they are compatible. And D2 and R1, they are compatible. So that's the goal. The two of these people, the donor and the recipient, who are incompatible, they enter the process and they're trying to find some other pair with which they're compatible. And so, oh yeah, before I mention the next part. So one thing that you might wonder is if we can't find a pair that's compatible with this pair, can we just do like 3 pairs? So can we do some kind of cycle where, like for example, if we had a D1, R1, D2, R2, D3, R3, is it okay if we have like D1, R2 are compatible, D2, R3 are compatible, and like D3, R1? Would that be okay? So like making some other kinds of cycles here. And I mean, yeah, I mean, you can kind of think of it as a cycle with the graph that we're about to construct. So they don't generally want to do that. So they want to avoid having these chains of pairs with 3 or more pairs. So having a D1, R1, D2, R2, D3, R3, it requires more operations. So with the 2 pairs, you have 4 operations because there's 2 donors, 2 recipients, all the people are getting operations. With 3 or more pairs, you're increasing the number of operations, but also the big issue is that there's a higher chance at least one person is going to back out of it. Like they change their mind and not want to do it, and then that messes up everything. So this is why you don't want to have a lot of pairs, because if a single person backs out, then you have all these other people who it messes it up for. So generally, they want to find just a single pair. Well, I said that wrong. A single pair of pairs. So a pair with a donor and recipient and another donor and recipient. So not 3 or more pairs, but just 2 pairs, a pair of pairs. And so if we're not going to consider the chains with 3 or more pairs, because these require too many operations and more chance someone's going to back out, then the problem that we're trying to solve here, we can think of it as we have a graph, and instead of having people as the vertices, we have pairs as the vertices. So our vertex set, this graph G, VG, is going to consist of a bunch of pairs, like D1, R1, D2, R2, D3, R3, and so on, however many pairs we have in the process. And there will be an edge between pairs whenever the pairs are compatible. So whenever we have, if we have a DI, RI, and a DJ, RJ, where DI is compatible with RJ and DJ is compatible with RI, then in that case, we put an edge between these vertices, DI, RI, and DJ, RJ. That's how I'll draw that edge, I guess. Maybe it's non-standard, it's all right. So that's our vertices, that's our edges. So we're not taking people as vertices. We are taking these pairs of people as vertices, a donor and a recipient pair. So each of those donor recipient pairs is a vertex. We put edges between the pairs if DI, RI, and DJ, RJ are compatible, if those two pairs are compatible. And then what we're trying to do here is we're trying to find a maximum matching in the graph. So we're just looking for what's the largest matching we can find, because this will save the most people. So that's the goal. We're just trying to save the most people, and maximum matching we can find, this gives us a way to save the most people. And the whole graph is just based on the compatibility of the pairs. So if we can find a maximum matching, all we have to do is just construct that graph and find the maximum matching, and that gives us the most number of people that we can save based on this compatibility, and also based on the rule that we're not going to take these chains of length 3 or more. So that's one interesting application. I thought that one was really cool, and there's plenty of other applications as well. So I wanted to start out on the math side of it just by looking at a 0-1 integer linear program for finding the maximum matching. So when we're finding a maximum matching, we're deciding which edges in our edge set to include. So we're given some graph G with vertex set V and edge set E, and our goal is to find a maximum matching. So we're trying to pick the largest possible set of edges so that all of those edges have no vertices in common. So like we were doing when we were looking at the ILPs, the integer linear programs in class, we can make these variables, and the variables will take on values 0 or 1 because we're doing a 0-1 ILP. So the variables will take on values 0 or 1. And these variables will correspond to edges because we're trying to find some set of edges. So each edge E will have some variable XE. XE will be 0 or 1. And XE being 0 means we're not including it in our maximum matching. And XE equaling 1 means we are including it in our maximum matching. And so that's that bullet right there. And I will write the other part of what I said here. So XE, we can think of it piecewise. It's going to be 1 if E is in the matching. And we'll make it 0 otherwise. And so if we want to find the size of a maximum matching in G, what we're trying to do is maximize the sum of the xe's over all of the e's in our edge set, big E. So we're trying to maximize that sum, but we have some restrictions because matchings must satisfy some properties. So we're trying to maximize this sum of the xe's over all the e's in the edge set, subject to these restrictions. So these restrictions for each vertex in the vertex set of our graph, we have a single inequality, and the inequality we write it as a sum. So for that vertex, we take the sum of the xe's over all of the edges E that contain the vertex V. So we're including in this sum all of the edges that contain vertex V, and our requirement is that the sum of the xe's for these e's that contain V must be less than or equal to 1. So this requirement, this inequality, in words, what it's forcing is that at most one edge containing V is in the matching. And this makes sense with the definition of matching because a matching cannot have any two edges with a common vertex. So for every vertex in our graph, we must require that at most one edge containing that vertex can be in our matching. And we require this for every single vertex in the graph. So each vertex in the graph gives us a single inequality. So the number of inequalities here in the restriction in these constraints is the cardinality of the vertex set. So that's a 0-1 integer linear program for finding a maximal matching. So on the last slide, we saw an integer linear program for finding a maximum matching. Here, we're going to look at a really simple greedy algorithm for finding a maximal matching. So this is different than the last slide. So this matching, it doesn't have to have the largest size. It just can't be a subset of any other matching in the graph. So it's maximal, not maximum. So we're going to discuss a real straightforward greedy algorithm for finding a maximal matching in any graph. We will build our matching as some set S. We'll call it S. So it'll be a set of edges, and we'll start it as an empty set. So in the beginning, we initialize S to be the empty set. Then we take all our edges in some order. So whatever our edge set is, we can pick some arbitrary order of the edges, or if we're given this graph, like it's an input to this algorithm, then the order has already been provided for us. So we can just go with the given order. So in the order of those edges, so for the edges in our edge set going in whatever the given order is, we will look at that edge. So that edge E, we'll see what vertices are in that edge. So E, we see the vertices are U and V, whatever U and V are. And so U and V will be the vertices in this edge E. So for each edge, we can just look at it and say, here's the two vertices in it. And then given those vertices, we can look in our current S. So our S, we're building it. So we can look at what S is currently, and we can see, are there any edges already in S which contain U or contain V? So if there is no edge that's already in S, which contains U or contains V, then we will add E to S. And we'll only add E to S if there's no edge already in S for which U is an F or V is an F. If there is an edge F already in S which contains U or contains V, then we do not add E to S. So this add E to S, it only applies if this part is true. So this only happens, E getting added to S, as long as the if condition in the bullet preceding it is satisfied. And I have a problem for you to think about related to this greedy algorithm. When the algorithm finishes, so when we get through the whole list of edges and we have this matching at the end that we've built, why do we know that the matching that we've built with this algorithm is actually a maximal matching? So why do we know that we can't add any edges to it and still get a matching? So I'll let you think about that. And I'll just note again that this matching, it's only maximal. It's not maximum necessarily. It could be maximum. So in graphs where all of the maximal matchings are maximum, then this algorithm will give you a maximum matching because it'll give you a maximal matching. And if maximal matchings are maximum, then that's a maximum matching. But if you have a graph that has some matchings that are maximal but not maximum, then this algorithm is not guaranteed to give you a maximum matching. It's only guaranteed to give you a maximal matching. So we're going to talk a little bit more about maximum matchings now. In order to state and prove a result about maximal matchings, I want to introduce a little bit more terminology. So this term is augmenting path. And we've actually kind of seen this on an earlier slide without saying it. So we didn't see the full definition of it on an earlier slide. We only saw some example. So first definition, and this is just a definition that we're going to use in the definition of augmenting path. We'll call a vertex in our graph free for a given matching M if it's not an M. So we had this picture before, the P4 that was on an earlier slide. And we picked this maximal matching. That was one of the ones we looked at. It's maximal because we can't add any edges to it. For that maximal matching, if that's our M right here with just a single element, then this vertex right here is free. That's free. And this one at the end is also free. These two in the middle, they are not free. And I should be a little more specific here. So the wording I use here, a little vague. I think it's clear what it's meant, but I'm just going to mention something. So we call a vertex free for a matching if it is not in M. So really what I should say there, if it is not in an edge in M. But hopefully that was already clear. If it wasn't, that's what I mean there. If it's not in an edge in M. So when I say vertices in M, I mean the vertices that are in edges in M. If I say that at any point later or earlier in the slides. So I should erase that a little. So an augmenting path for the matching M, and I'll keep this P4 up here. An augmenting path is a path that starts and ends at free vertices. And the path alternates between edges in and not in the matching M. So for example, if we wanted to find an augmenting path for this M right here, we could take this whole graph. And that gives us an augmenting path because the path starts and ends at free vertices. And the edges alternate between being not in M and being in M. So the first edge, by definition for an augmenting path, the first edge has to not be in M because it contains that free vertex. Then the next edge has to be in M, and the edge after that has to be not in M. And it could keep on going like that. So whatever the length of the path is, it's going to have an odd number of edges on it. We can look at another example that's a little larger. So here's a P9. P9, we can pick some matching here. So we can take this matching, for example. So these edges are disjoint that I'm choosing. So I'll take 3 edges, I guess. And we can see that there are a number of free vertices here. So our free vertices, this one's free, this one at the end is free, and this one actually at the end is free. Now, if we want an augmenting path here, we could take, for example, this path. So that gives us an augmenting path there because it starts and ends at free vertices, and the edges alternate between being not in and being in M. So first edge here, not in M, second edge in M, third edge not in M, fourth in, fifth not, sixth in, seventh not, and that's all the edges. Let's look at one more example, and then we will continue. So last example here. Okay, so we got a cycle here. I think I made a C13 there. Okay, and then I'll pick a matching here. I'll do one that's a little weirder than the others. Okay, yeah, that seems fine. So we got a matching there. So that's fine. And now we can see some augmenting paths for this matching. So that's our matching M. And here's one augmenting path. So there it is. So this one is free, that vertex. This one's also free. And you can see the edges on that path, they alternate between being not in M and being in M. So first one's not in, second one's in M, third one's not in M, fourth one's in M, and this fifth one's not in M. Now there's other augmenting paths in this graph. So let's see if I can use the eraser effectively, okay? So here's another augmenting path. So we'll start at this one. And this is an augmenting path for this matching M. So it's different augmenting paths for the same matching. There we go. So you can see both the starting vertex and the ending vertex for this path are free. Moreover, the edges, they alternate between being not in and being in the matching M. So first one here is not in, second one's in, third's not in, fourth's in, fifth's not in. So I think that's hopefully a sufficient number of examples for an augmenting path. I thought this last example was important because it shows us an augmenting path that does not have the full matching on it. So let's continue then. Okay, so examples. I guess I already did those path examples. And we can also do a grid, I guess. So I did have a certain grid in mind. So let's take this small grid, a 2x(n) grid. You can barely call it a grid even. Okay, and we're gonna take a matching here. Actually, I'm gonna take a slightly different matching. I'm gonna do this one. I'll leave those outer ones out. Okay, now let's find an augmenting path on this one. So we do have some free vertices. I guess I'll point out the free vertices first. So right there, we got a free vertex. We also have one higher up right here. And of course on the other side, same deal over there. So here is one augmenting path that we could do. We could start at this one, and then we can do this kind of like snake path here. Hopefully I won't mess up drawing this. We'll see. Okay, here it goes. Okay, I think that might be okay. Yeah. So our start and our end vertices, they're both free. And our edges, they alternate between being not in and being in the matching. So M will be our matching. First edge is not in it. Second edge is in it. Third edge is not. Fourth is in. Fifth is not. Sixth is in. Seventh not. Eighth is in. Ninth is not. Yeah, so that's good. And you can also see, I won't draw this one because it's symmetric, but you can see that we could have also taken another augmenting path. So we could have taken, I guess I will draw it, but more as a scribble. We can take another augmenting path, which starts at this vertex, and it goes like this. And then it finishes here. So it finishes there, starts there, and it just goes in the opposite directions as this path that I drew first. So that gives us several examples of augmenting paths. So now that we have discussed the definition of augmenting paths, we're ready to discuss this result about maximal matchings. And it's called Burge's theorem. I've also seen it called Burge's lemma, but I think we'll call it Burge's theorem here because we're going to prove a lemma that will help us prove Burge's theorem. So it'll be better to have a lemma and a theorem instead of two lemmas. And this is the statement of Burge's theorem / lemma. A matching M is maximum. So just to emphasize here, maximum we're talking about, maximum, not maximal. So this is more exciting than maximal, it's maximum. So the matching is maximum if and only if it has no augmenting path. One direction of this will be pretty straightforward, like pretty simple. The other direction, it's not too bad, but we're going to be using the lemma for the other direction. And the lemma, it's not like the lemma takes much to prove. It's going to be real straightforward for the lemma. It's just that it's going to be a little nicer to have that lemma instead of trying to prove the whole lemma in the middle of the proof. But before we even get to lemma, we can already do one of the directions here. So why is this true? Well, let's look at one of the directions before we do that lemma. So the forward direction, this is going to be the easier direction. So in order to prove the forward direction, we want to prove if M is maximum, then it has no augmenting path. So if we want to prove that, we can prove it's contrapositive. So we want to get a contrapositive, then we have to show that if M has an augmenting path, then M cannot be maximum. So we will assume that M has an augmenting path. And we need to use this path to prove that M is not maximum. So the idea is we're going to take this path and use it to construct a matching in the same graph that is larger than M. And we're going to use the definition of augmenting paths in this. So an augmenting path, I'm going to draw just an example here. So we got some augmenting path. So it starts and ends with free vertices. So free vertex here, free vertex here. And it's a path, so it has edges between the successive vertices on the path. And then it has to alternate between edges not in and edges in M. So the first edge has to be not in M, and same with the last edge, because the first and last vertices are free. And that tells us exactly which edges are in M and which are not in M. I gotta put an extra vertex here. That's our free vertex at the end, actually. Make that arrow. Yes, that will be better. So as you see, we have free vertices on the front and end, and the edges alternate between being in M and not in M. So our M, and there's possibly more M out here. But these are not part of the augmenting path. So we see we have 3 edges of M on this path. In general, it's going to be J edges of M on the augmenting path for some J, and J plus 1 edges not in M. And that's because the edges are alternating on the path, and the edges start and end with edges not in M. So there's an odd total number of edges, and that means that the number of edges not in M on the augmenting path has to be 1 more than the number of edges in M on that same augmenting path. And so we're going to take that augmenting path and we're going to use it to build the larger matching. And what we can do, since this vertex is free right here, we know that it's not used in any of the edges in the matching of M. Same with this vertex here. It's not used in any of those edges. Moreover, this vertex here and this vertex here, the only edges in the matching that can use it are like these edges right here, like this and this. Those edges are in the matching. Those are the only ones that can use it because it's a matching, so it can't have common vertices. Same with these vertices here. The only edges in the matching that are using them are this edge is using this one, and this edge right here is using this one. So what does this tell us? Well, we can make a new matching by replacing the edges on this augmenting path that are in M with the edges that are not in M. So here's our replacement edges. So we're just going to take all of the M that's outside the augmenting path. So we'll include these, and then we'll include the ones on the augmenting path that are not in M instead of the ones that are in M. And the check mark is the new matching. So the edges that I denote with the check mark. So we take all the edges in M that were not on the augmenting path, like these edges up here. And then we take the edges not in M that are on the augmenting path. And the next bullet, I say that in words. So I'm actually gonna move this thing that I drew here, this check mark. I'll put that up here. Okay, that should be good. So like I wrote up here, the augmenting path has j edges of M, and we construct the new matching using the other j plus 1 edges on the augmenting path that are not in M. So the ones that are not in M, the ones that I drew rectangles around instead of circles. So maybe I have too many arrows now there. I'll erase them all, I guess. They're not really doing much. They're only there to point to things, but they should disappear after that, I guess. So that gives us a new matching. And it's because none of the edges in this new matching have any vertices in common. And we talked about that because these starting and ending vertices were free. So using those in this new matching is fine. And using all of these other vertices, so this vertex here, this one here, so all these vertices that we're using in this new matching, we can also use them because they were only being used before by these edges in M that were on the augmenting path. And we got rid of those edges, so we won't have any edges in the new matching that have vertices in common. And another way we can write this, we can use a symmetric difference to write this new matching. So the new matching, I guess I use a check mark to denote it. We'll call it M prime, the new matching. And we can write M prime as this symmetric difference. So we take the old matching M minus the augmenting path plus the augmenting path minus the old matching. And the symmetric difference, we're talking about sets here. So we're talking about sets of edges. So M's a set of edges. We're thinking of P, the augmenting path, as a set of edges. And then we're just doing M minus P plus P minus M. So we're just using the symmetric difference from set theory. And that's exactly what we've described in this last bullet. So this last bullet, we are doing the symmetric difference there. So we're taking the remaining edges of M that are not in P. That part is this right here. So I'll call that 1. That's the 1. And then this part right here, the P minus M, this is the J plus 1 edges on P that are not in M. So we'll call that 2. And J plus 1 edges of P that are not in M. So that's 2 right there. So it is the same thing. It is just a symmetric difference that we've just constructed for that larger matching, M prime. And M prime, it is larger because we started with M, however many edges M has, and we replaced exactly J edges of M with J plus 1 edges that were not in M. And we left all the other edges that were in M alone. So we just took J edges that were in M and replaced those J with J plus 1. We didn't change the rest of M, so the size went up by 1. So M prime, it's a larger matching than M, so that means M is not maximum. So that gives us the forward direction. So forward direction, it's not too difficult. We only took a few steps on that. We just had to do a small construction using our augmenting path. But the construction, it was pretty natural construction. It was just a symmetric difference. So now we gotta figure out how we're gonna get the backward direction. And that's the one that I said we're gonna prove a special lemma for that. But the lemma, it's not like an exciting, difficult lemma. It's just gonna be just a few lines. Although maybe saying a few lines, maybe that's underestimating it a bit. So here's the statement of Burge's theorem again, and the backward direction is what we have left. And the next bullet, it's going to say, got to prove a lemma. Yeah, we'll prove the lemma for it. So let's see, what is this lemma that we're going to prove? Well, here it is. So I call it the symmetric difference in matchings lemma. I made up that name for it. I think that name describes it pretty well. So we'll suppose that we have two matchings in the same graph. We'll call them M and N, and we'll say that our graph is G. And we're going to look at a subgraph of G, and it's going to have the same vertex set as G, but the edge set is going to be the symmetric difference. So it makes sense. When we did the forward direction, we used the symmetric difference to construct a larger matching. So we used the symmetric difference. It was kind of our key substance of the proof to prove the forward direction. And so it makes sense here for the backward direction. Symmetric difference, it might factor into the backward direction as well. So this is why we're looking at the symmetric difference. And here's the claim for the lemma. So the lemma, I haven't stated what the lemma is claiming yet. This is just the setup for the lemma. So the lemma is claiming that the connected components of this subgraph are going to consist of isolated vertices, even cycles with edges alternating between the matching M and the matching N, and paths that have edges alternating between the matching M and the matching N. I claim those are the only three kind of connected components that we can have in this subgraph. And so we need to prove that. So why is it true? Part of the proof, a pretty simple part of the proof, I'm going to leave to you to think about. And it's the one that's in the next bullet, I think. So actually, no, not the next bullet, the bullet after this one. So this bullet, each vertex in this subgraph has degree at most 2. So we can see that pretty easily because we can look at the edges that we're including in this subgraph. So the edges are going to be edges from M and edges from N. And it's not even all the edges from M and all the edges from N. It's only the edges from M that don't occur in N and the edges from N that don't occur in M. So we're not including stuff in their intersection, for example. So the claim is each vertex in this subgraph has degree at most 2. And that's because when you restrict the subgraph just to the edges of M or just to the edges of N, each vertex has degree at most 1. So each vertex has degree at most 1 in the matching M and degree at most 1 in the matching N. So when we take this subgraph, which has an edge set, which is a subset of the union of the edges of M and N, each vertex can only have degree at most 1 plus 1, which is 2. And so here is the problem for you to think about. Prove that any graph of maximum degree at most 2 has connected components that are isolated vertices, paths, and cycles. And I want to clarify this wording here. So this wording, I thought it was clear when I wrote it, but I guess one possible interpretation, some people might think that this is saying that graphs of maximum degree at most 2 must be isolated vertices, paths, and cycles. And when I say consists of, I mean the connected components of them are. So the connected components of these graphs are isolated vertices, paths, and cycles. So prove that any graph of maximum degree at most 2 has connected components that are isolated vertices, paths, and cycles. And we're going to use that in the next bullet, but I should probably move these words over a little. Weird, okay. So I'll erase that, and then I'll move that. Okay. There it goes. Okay, that should be good. So we're going to use that problem that you're going to prove if you want. And we're going to use that to finish off this lemma. So to get the statement that we have here. And we can see the statement we have here, it's kind of close to what we have with the problem. So the problem is telling us that in the subgraph H, all of the connected components are isolated vertices, paths, and cycles. And up here, we're trying to prove that all the connected components are isolated vertices. So we already got that part. That first bullet of the lemma is finished. But then it has to be a little more specific for these last two. These last two, it's not just cycles, it's even cycles with edges alternating between M and N. And the last one is not just paths, but paths with edges alternating between M and N. And we can see that the edges have to alternate between M and N in this subgraph H. So if H does have any path or any cycle which have more than one edge, so cycle by definition has to have more than one edge, the edges, so if we have a path, for example, I'm just going to draw a path here. If this edge is an M, then this one has to be an N, because that one can't be an M. And all the edges in this subgraph H are from M or N. And if this one's an N, this one has to be an M. And it keep on going like that. So on the path, oh, whoops, I wrote the wrong one there. It should be an N. So on the path, the edges have to alternate between M and N. And if this one started as an N, then we would get an M here, and then an N, and then an M, and so on. Now we can look at a cycle. So we'll take a pretty small cycle here. So let's say this one's an M. Then this one can't be an M because can't have any vertices in common in M. So this one has to be an N because all these edges are from M or N. This one's same thing. It can't be an M because the vertex here would be in common. It has to be an N because all the edges are from M or N. This one has to be an M. This one has to be an N. And then this one has to be an M. If we start with this one as N, then we would get M here, N there, M here, N there, and an M here. Now, for the cycle I drew there was an even cycle. I could have drawn an odd cycle. So for the odd cycle, if we try to start with this as an M, and then this would have to be an N, and an M here, an N there, then we got an M here, we got an N here, and then we get an M next to an M. This would be a problem. Can't have that in a matching. And if we start with that one as an N, it would have been the same problem. We would have gotten two N's next to each other. So even cycle, it has to be an even cycle. It can't be an odd cycle. Because if you had an odd cycle, we would be forced to have two edges from the same matching next to each other because the edges have to alternate, but then they couldn't alternate when it's odd. So this is why it has to be even cycles. And that gives us the whole statement of the lemma now, because we know the edges have to alternate between M and N, and we had paths, we have even cycles, we have isolated vertices. So that finishes it off. So now we're ready to do the backward direction of Berge's theorem. There's the statement of the theorem again. And the backward direction, we will suppose that M, this matching M, has no augmenting path. And we'll do a proof by contradiction here. So we'll assume that there's some matching M, some matching N, not M, that is larger than M. Because what we'd be trying to prove here, we want to prove there's no augmenting path for M, then M is maximum. It's a maximum matching. In order to prove that with a proof by contradiction, we can assume that M is not a maximum matching and use that to get a contradiction. And assuming that M is not a maximum matching, to do that, we just have to assume that there's some matching that's larger than M. So we'll assume for contradiction that we have some matching in the same graph. We'll call it N instead of M, and it's larger than M. And now we're going to try to use that last lemma we just proved. So we're going to build the symmetric difference of M and N. So we'll take the subgraph of our graph G, which has vertex set the same as G, but the edge set will be the symmetric difference of these two sets of edges, M and N. And they're matching, so they are just sets of edges. And as we proved on that last slide for that special lemma, the connected components of the subgraph H, they're going to be isolated vertices, paths, and even cycles. And the edges on the paths and cycles have to alternate between M and N because M and N are matchings. So M can't have any two edges with vertices in common, and same with N. N can't have any two edges with vertices in common. So these are our connected components. We have isolated vertices, we have even cycles, and we have these paths. So the isolated vertices and the even cycles, if we think about how many edges from M and from N are used on these, well, the isolated vertices, no edges are used there because they're isolated vertices. The even cycles, same number of edges, same number. Let me make that a little more legible. Same number edges from M and N on those even cycles. And so these paths are going to be helpful to us. And the reason why they're helpful is because N is larger than M. And that tells us that one of the paths must have more edges from N on it than from M, because the isolated vertices can't have more edges from N than M because they have no edges. The even cycles can't have more edges from N than from M because they have the same number of edges from both M and N. And that means the only place where we can have more edges from N than from M is on these paths. And that means that at least one of the paths must start and end with edges from N. And moreover, like I said before, on all of these paths and cycles, the edges have to alternate. And this path right here, we can see this is a real special kind of path. The edges alternate between M and N. So I'm going to draw a picture of this path, an example of this path, of course, because I can't draw all the paths like this. It would take infinitely much space, but I better make it a little longer there. There we go. Okay. And this path has more edges from N than from M. So here's an edge from N, and then an edge from M, then an edge from N, M, N, M, N. Okay, and this one here and this one here, they are both free for M. So they're not free for N, not free for N, but they're free for M because no edge in M contains either of those two. And we can see that these edges alternate between being not in M and being in M. And then that means that this whole thing right here, what do we have there? We have, it looks like we got an augmenting path for M there. So that's an augmenting path for M, but we assumed that there's no augmenting path for M. That was our assumption here. So we're trying to prove the backward direction there. So we're saying M had no augmenting path there. So that means that we just got a contradiction. We built an augmenting path for M, but M has no augmenting path, so contradiction. And that tells us that since we got a contradiction, it means that our assumption for the contradiction was a false assumption. And that false assumption was that there is a matching N in G that is larger than M. So that assumption is false. So that means then that M has to be a maximal matching. So M, we'll write this at the bottom, M is maximum. And that completes the proof. So we did both directions of it, forward direction and the backward direction. So now we're going to look at some simpler things. So there's this parameter called the matching number, and we'll define that, and it's just based on some definitions that we've already seen. The matching number is the size of the maximum matching in the graph. and we call it nu of G. And for all graphs G of order n, we get this immediate upper bound on the matching number. Nu of G is less than or equal to n over 2. And that's because we cannot go over n over 2 edges with no vertices in common in a graph of order n. So if you had nu of G, if it was greater than n over 2, all the edges being disjoint, implies that there are over n vertices in the graph. And that would be a contradiction because G has order n. So since there's no vertices in common in any of these edges, we must have the matching number of any graph of order n be at most n over 2. And this n over n here, why is it over n? I'm just going to say that's 2 times n over 2. Because if we have more than n over 2 edges, then we have more than 2 times n over 2 vertices in this graph, since all the edges can't have any common vertices. And it is possible to attain this bound, but you can only attain this bound if you have a matching contain every vertex in your graph. So the only way to attain that, to have nu of G equal n over 2, that would mean that the matching contains exactly 2 times n over 2 vertices. Because any matching can't have any vertex occur in 2 edges of the matching. Each vertex can only occur in at most 1 edge of the matching. So if the matching attains this upper bound, if it's actually matching number n over 2, then that's a matching with all the vertices in our graph. And that's a special kind of matching. So if you do have a matching with all the vertices in the graph, you call that a perfect matching. So perfect matching just means that every vertex in the graph is used. It's a matching that contains every vertex. And one thing that's pretty clear here, the perfect matching for a graph of order n, it has to have n over 2 edges. And since it has n over 2 edges, that means that n over 2 is an integer in a perfect matching. So perfect matchings can only happen when n is even. So they can only happen in graphs of even order. And we'll look at some examples. So in a cycle here, let's consider so here's a cycle. So we can find multiple perfect matchings in this one. Here's one perfect matching. And that contains all of the vertices and the edges of the matching. Another perfect matching, we can do it with rectangles. So both of those are perfect matchings. And a grid. So we can look at another grid. So we can take this matching. This is another perfect matching. And this also tells us the matching numbers of these graphs. So if this is our graph G up here, this is our graph H down here. We see that the matching number of G, that's going to be the size of a maximum matching in G. We know it's at most the number of vertices over 2. And we can see that that's attainable here. So we attain that with 2 different constructions. So it's 3 here because 6 over 2 is 3, and we can attain 3. So we got 3 there. This one we see it has 10 vertices. So we know the matching number is going to be less than or equal to 10 over 2, which is 5. And actually, the matching number equals 5 because we can attain that 5. So our construction right there attains 5. So it equals 5. So continuing with the matching number, we can express the matching number in terms of a parameter that we've seen before. In order to express it that way, we're going to use this graph that we've seen before called the line graph. So L of G, this is the line graph of G to review. This is the graph where the vertex set equals the edge set of G. And in this line graph, we put edges between 2 vertices, E and F, in our line graph, only if the edges E and F in G had a vertex in common. So that's just the definition of a line graph for any given graph G. And to review, let's look at some examples of line graphs. So let's consider a star. We'll just take like a K14. And it has edges, we'll say E, F, G. We'll do a G there and H here. Okay. And then we're going to build a line graph of K14. So L of K14. And we're going to draw it like this. So it's going to have 4 vertices for each of the edges of G, each of the edges of K14, I mean. So E, F, G, H. And then we put edges between any 2 vertices that have a vertex in common in K14. So E and F, this edge is F, this edge is E. Do those 2 edges have a vertex in common? They do. That vertex is the one in common. So E and F get an edge between them. Same with E and H. E and H have that center vertex in common. So E and H get an edge. Same with E and G. They have that center vertex in common. So all of these edges, E, F, G, and H, they all have the center vertex in common. So we put edges between all of them. So we get right here, that's going to be a K4. So with the star of order n, you get a complete graph of order n minus 1. So a K1n, its line graph is going to be a Kn. So a star of order n plus 1, our line graph is a complete graph of order n. Okay, so that's one example. And let's look at another example of a line graph. So we'll make our edges A, B, C, D, E, F, and G. And then we'll draw our edges around a circle, I guess. Might as well, because we had a cycle up there. Hopefully it'll end up looking nice. And then we'll put an edge between the 2 vertices in this line graph. So we had C7 up here. We have L of C7 down here. We'll put an edge between 2 vertices in this line graph only if the corresponding edges in the original graph had a common vertex. So we'll look at A right here. So A, this edge, it has a common vertex with that edge B and a common vertex with the edge G. So A gets an edge to B here, A gets an edge to G there. Then we look at B here. So B, there's our B. B, we already know it has the edge with A, but it also has a common vertex with C. So it has an edge to C. Then we look at C. C has the edge to B. It also has the edge to D because it has a common vertex. It keeps on going like this. So we can just get another copy of C7. So L of C7, we get C7. So if you take a cycle of order n, you take its line graph, you get a cycle of order n back. And the reason why we're talking about line graphs here is because the matching number of the graph G is just the independence number of the line graph of G. And if you think about that, the reason for this is we're just trying to find a maximum set of edges such that none of these edges have any vertex in common. So a maximum set of edges in G with no vertices in common. And that's the same thing as a maximum set of vertices of L of G. So max set of edges in G with no vertices in common. So the size of that set, so the size of that max set is going to be our nu of G. And this is the same as the size of a max set of vertices of L of G. And the edges in G are literally the vertices in L of G. So what we just switched there, that's just by definition. So edges in G to vertices of L of G. And these vertices of L of G have no edge between them. And that's by definition of line graph. So we know that if the edges in G have no vertices in common, then the corresponding vertices of LG will have no edge between them. And vice versa. If the vertices of L of G have no edge between them, then the corresponding edges in G have no vertices in common. So a size of a maximum set of edges in G with no vertices in common is the same thing as the size of a maximum set of vertices in the line graph of G with no edge between them. And this right here, that's just an independent set. Independent set in L of G. So we're just trying to find the maximum size of an independent set in L of G, and that is the independence number of L of G. So we can think of this matching number just as this parameter that we've seen before, the independence number. And one last piece of terminology, which is going to give us a relation with the matching number. So it's an interesting relation that's kind of similar to one that we've seen before. So we saw a relation between the independence number and the vertex cover number. And now we're going to see a similar kind of relationship between the matching number and something called the edge cover number. So we talked about the vertex cover number. Now we're talking about an edge cover number. So an edge cover S of G is just a set of edges of G such that every vertex in G is in at least one edge in S. So it's analogous to the vertex cover. So the vertex cover was a set of vertices such that every edge in the graph is adjacent to some vertex in the cover. So here we're having a set of edges such that every vertex is in at least one of the edges. So totally analogous to the vertex cover. And we can consider some examples. So let's take a complete graph, a small one. So if we want an edge cover, we want every vertex to be in at least one edge in here. Then here's an edge cover, for example. Psych is an edge cover because all the vertices are in at least one edge, because this one is in this one is in this, and those two over there in the other one. And we can also look at a larger complete graph. So we could take complete graph of order 5. and we can take this edge, we can take this edge, and then the last edge is going to have some overlap with one of the earlier edges. So for example, could do this one would be fine. That gives us 3 edges, and it covers our graph, because every vertex is in at least one edge. And based on edge cover, it's natural to ask, what's the smallest edge cover we can find? And we have a term for that, a minimum edge cover, and it's just an edge cover of minimum size in the graph. And we can see in the examples up here, to cover all of the edges in the graph, or to cover all the vertices in the graph, sorry, our edge cover has to have at least, so the edge cover has to have at least n over 2 edges here. So number of edges in the edge cover has to be at least n over 2 for a graph of order n. And that's because every vertex in your graph has to be in at least one edge, and each edge can contribute at most 2 vertices. So the number of edges has to be at least the total number of vertices over 2. So the number of edges in an edge cover of a graph of order n must be at least n over 2. And we can see that in the examples here. So we got an edge cover of size 4 over 2 here equals 2. So the bound is attained for that example. This one right here, 5 over 2 equals 2.5. So the bound can't be attained when you have n odd, because the number of edges in the edge cover has to be an integer. And if n is odd, then n over 2 will be a half integer. But if n is even, then we can possibly attain the bound, depending on the graph. And just like we had a parameter for the matching number, we also have a parameter for the edge covering number. So the edge covering number, and this is rho of G, we'll call it, it's the size of a minimum edge cover of G. So we can see, for example, up there with the K4, the edge covering number of that is just 2. And with the K5, the edge cover number of that was 3. So we know that the K4, its edge cover number had to be at least 2, and we found an edge cover number with exactly 2. So it's equal to 2. With the K5, we know its edge cover number had to be at least 2.5, and that means it has to be at least 3, because it can't be a half integer. And it's at least 3, and we showed that we can attain it with 3. We can find an edge cover of size 3 that contains all the vertices. So that means that the edge cover number of K5 is 3. And here's a problem for you to think about. So I said that there is a result related to the matching number and the edge cover number that is very similar to a result that we saw in an earlier video about the independence number and the vertex cover number. And here it is. So prove or disprove this in a graph G of order n with no isolated vertices. Prove or disprove that the edge cover number of G plus the matching number of G is equal to the order of G. And we saw that with this example with the K4. So the K4, the matching number of K4 equaled 2. So the size of a maximum matching in K4 is 2, because we can just take 2 edges, like the 2 edges I drew here. These 2 edges give us both an edge cover and a maximum matching. So we see that the inequality is true for that example. And that example has no isolated vertices, so it makes sense. So see if it's true in general for all graphs with no isolated vertices. And that brings us to the end of the video. Thanks for watching.